As an application to graph theory, I'm going to show you the list coloring problem. So for those who took the graph theory course, you may recall the definition of the list coloring. But nevertheless, let me state the definitions. So in the usual coloring, each vertex has the same set of available colors, let's say from 1 up to k. And then the coloring, k coloring of a graph is assignment of colors for each vertex such that adjacent vertices get distinct colors. In the list coloring, each vertex may have distinct set of colors available. So that color is written as L. So let L be a mapping that maps a vertex of G to a set of let's say LV of colors available to V. And then we say a coloring C from VG to union of LV is an L list coloring if whenever V and W are adjacent, CV is not equal to CW, right? So the adjacent vertices get distinct colors. So that's L list coloring, and we say G is L list colorable if it has an L list coloring, or sometimes called L choosable. It's the same thing, right? And then now the definition, the list chromatic number. Oh yeah, let's and we say G is K list colorable or K choosable if for any list assignment. So this is this is called the list assignment. For any list assignment L of G with each vertex having list and list K, G has G is L list colorable, and then the list chromatic number written as chi L of G, or sometimes called the choice number. So depending on the paper, sometimes some people use chi L and some people use CH of a graph G is the minimum K such that G is K least colorable. Okay, now this is easy to see that the least chromatic number is a least chromatic number because if your graph is K least colorable, then if you give the same set of list for each vertex, then that's a usual coloring. And so the chromatic number is a minimum k such that graph is k colorable. So if this is graph G is k least colorable, then it's k colorable. So therefore the chromatic number is at most k. But this gap could be arbitrary. So one example is k2, 3 and 1, 2, 1, 3. So I give this list for each vertex. And I know that this graph k2, k3, 3, it's not 2, 3, 3, 3. Chromatic number is 2, it's bipartite, so it's 2 colorable. But however, the least chromatic number is not 2. Why? If it's 2 least colorable, then with this list assignment, you must have coloring. So let's say I color by symmetry. Let's say I color this by 1. Then you cannot use 1 here. We cannot use 1 here. That means the only choice I have is 2 and 3. But since I use 2 and 3, I cannot use 2 here. I cannot use 3 here. Then this vertex is no more choices left. So therefore, this graph is not true least colorable. And you can make an arbitrary big graph. So if you have a complete bipartite graph with a large number of vertices, chromatic number is 2, but the least chromatic number is big. Now, what we are going to show is a theorem due to Allon and Tarski in 90s that the chromatic number, okay, so every simple bipartite planar graph. Well, I mean, simple doesn't change anything, because if you have parallel edges, it don't do anything, and we usually ignore loops for vertex coloring. It's 3 choosable. So in other words, planar and chromatic number at most 2 implies that least chromatic number at most 3. So without this planar condition, this is not true, right? If you take a large complete bipartite graph, the least chromatic number is bigger than any number you want. Okay, so this is the theorem we want to prove, and we're going to use combinatorial Lewis-Strand. And to prove this, we need several lemmas. Okay. Now, we'll talk about some orientations. Right. So, how do we prove this? Let me start with defining a few terms. We say a directed graph is Eulerian if the out degree at each vertex, the in degree is equal to the out degree. Usually in an undirected graph, we say graph is Eulerian if every vertex has even degree, but in a directed graph, we want more. Every vertex has same number of edges incoming with edges outgoing. All right. You may have a another vertex here with, let's say, 2 edges incoming and 2 edges, no, 2 edges outgoing. But anyway, so this, if this is the case, then we say the graph is Eulerian. Now let EE of D with the number of Eulerian subgraphs with subgraphs of D with even number of edges and with, I should say number of Eulerian subgraphs. I don't want to count all the isolated vertex. So let's say on the vertex set, so all these are spanning subgraphs, and EO T is the number of Eulerian subgraphs of D on the vertex set with D with odd number of edges. Right? So for instance, let me let's do some simple example. So how do I draw the Eulerian graph easily? Just make an Eulerian circuit. So this is Eulerian, and so what are the example of even Eulerian subgraphs? Well, think of the even cycles. For instance, this is even Eulerian subgraphs, and that's even Eulerian subgraphs. Right, and then their union or empty set is even Eulerian. Right. So I only need to look at this set of edges. And other Eulerian subgraphs, so these are even, and other ones are the, for instance, this is odd, right? And that's yes. So 1, 2, 3, 4, 5. That's also Eulerian. Yes, and then I think that's it, right? I mean, there may be more, but so here's the theorem. So let D be a directed graph on the vertex set V, V1, V2, Vn, and let Di be the out degree of Vi. Right, so let L be a list assignment such that L of Vi is at least Di. No, more than Di. So you want, I give a list assignment so that each vertex has more colors available than the out degree. And if number of even Eulerian subgraph is different from number of number of odd Eulerian subgraphs, then D is L least colorable as an undirected graph, right? So this is the theorem that we're going to prove, and this is the theorem that we will use to combinatorial new strands. So how do we prove that? So we assume that LV is as integers and the cardinality is equal to di plus 1. And if you have more colors available, we can just ignore a few colors. So let's assume that at each vertex the list contains exactly out degree plus 1 distinct integers. Now we define Fg of the x1, x2, xn be the product of xi minus xj, where whenever vi, vj is in ED. So, by the way, this is oriented, right? So whenever vi is adjacent to vj, we multiply xi minus xj. The goal is to show that Fg of x1, c1, c2, cn is non-zero for some choices ci in LVI for each I, right? If that's the case, then adjacent vertices get distinct colors, so we have coloring. And this is a perfect setting for using combinatorial new strands. So what is the degree? So degree of Fg is the number of edges. Right, that's the degree. But number of edges is equal to sum of the di's. Right? In a directed graph, sum of the out degree is equal to the number of edges. Let's assume the graph has no loops. Loopless. Yeah, otherwise doesn't make sense. The coloring has nothing to do with the loops. All right, now, so that means if we have a term like this, and this is the this term, this monomial achieves the maximum degree. So for us, it's enough to prove that the coefficients of this term, this monomial, is non-zero. Goal is to show that the coefficient of this is non-zero. All right. That's the goal. If that's the case, then we have an assignment like this thing by the combinatorial new strands. Now, let's consider the expansion. of this polynomial f of g. So now we need to look at the signs, right? So let dE of d1, d2, dn be the number of choices of ends of each edge, so that xi, right? I mean, what I mean is, at each edge, we're gonna choose this or that, right? It's either xi or xj. But in front of xj, you have a minus sign. So I'm gonna count that. So dE of d1 up to dn is the number of choices of ends of each edge, so that xi is chosen di times for each I, and the head, so -1, right? So if it's a head, then we multiply -1. Head is chosen even number of times. So this dE contributes positively to the expansion, and dO is the same thing, number of choices of ends of each edge, so that xi is chosen di times for each I, and the head, so -1, is chosen odd number of times. All right, then the coefficient of product of xi to the di is equal to dE d1, d2, dn minus dO, d1, d2, dn. So we need to show that this difference is non-zero. Now we claim that dE of d1, d2, dn minus dE of d1, d2, dn is equal to E of d minus EO of d. The number, the difference between number of even or orient subgraphs and number of odd or orient subgraphs. Now, to prove this, we find the bijections. So how do we find the bijections? So think of the some choices. So for every edge, we're gonna choose either tail or an right. Say yeah. So consider a choice, let's say x, of ends, so that xi is chosen di times at each I. So depending on the number of times where xi was had or not, this choice x belongs to dE or dO. Now let's say dx be the set of edges whose heads are chosen. All right. Now, initially, it was a graph like this. So in this case, di is 3, right? Because you have 3 outgoing edges. Now I know that this choice x choose this vertex 3 times. So you gotta choose, let's say you may choose 1, 2, 3. They chose this. Now dx is the set of edges whose heads are chosen. That means you're choosing this guy and that guy. So that's in dx. Now the thing is, yes. Now when you look at the set of edges whose heads are chosen, what do we know? Now, by the way, those two edges are also in dx because they didn't choose the tail, so their head was chosen, right? So these red edges are in dx. Now you see that at this vertex vi, the number of incoming edges is 2, number of outgoing edges is 2 in dx. So you will observe that dx is an Eulerian subgraph. Why? This is because, right, each vertex vi, you have some edges going out, some edges, and these, let's say these were chosen, the head of them was chosen and tail was chosen. And let's say this head was chosen, tail was chosen. Then what is in dx? So the number of edges here is di, and head was chosen, so these are in dx. And these are also in dx. But the thing is, x is chosen, so these edges, this vertex is chosen, and those edges, these vertices are chosen. So the number of times you choose v1 is this, right? So those blue edges chose v1. So the number of blue edges, no, not di, right? And number of red edges is that these are edges in dx. But you see that the number of blue edges is equal to number of blue edges is equal to di, because that we chose by these constructions. So therefore number of outgoing out degree out out degree of vi is equal to in degree of vi. Right, so the number of edges here plus number of edges there is di, number of edges here plus number of edges there is di, so therefore these two numbers are equal. All right, so therefore D maps X to an Eulerian subgraph. And in particular, if X belongs to, what was it, DE, then, so what does that mean? That means the head was chosen even number of times, right? So that means the head was chosen even number of times. The sum of the out degree or in degree, sum of the in degree is even. In dx. I mean, I don't have to say it this way, because dx number of edges in dx is even. If x is do, then of course number of edges of dx is odd. So that means it's a bijection, and that maps even to even and odd to odd. So dE d1 dn minus do d1 dn is equal to EE EED minus EOD. Alright, so this is kind of magic, that if you know that the number of even Eulerian subgraph, directed subgraphs, is different from number of other Eulerian directed subgraphs in a directed graph, then you can use that to prove that graph is L is colorable for certain L. Alright, now this is interesting, but now we want to prove it for bipartite graph. And how do we prove it? Here's a lemma. Actually, the planarity isn't play a big role. What we actually care is the density of the edges. So let's say G be an undirected graph, and let dg be the maximum density. So H is subgraph with at least one vertex. So for all subgraph, you look at the density of edges and take a maximum. Then there exists an orientation of G. So orientation of G means you want to attach a direction to every edge to make a directed graph, so that the out degree of each vertex is at most d of G. This is what you back type. So for instance, I mean, if you have double the number, then actually there's different consequences, right? So for instance, if the density is d, then the average degree is at most 2d. So you have a vertex of degree at most 2d. So you can find the vertex whose degree is at most 2d, and then you delete it, and the remaining you apply induction. So that means you have an ordering. So the first vertex you delete, you put it at the last vertex. So you orient every edge towards to that direction. So you orient every vertex, every edge instantly with this vertex away from it, and apply induction in the remaining. But that will give you an orientation where each vertex has out degree at most twice d. But in this lemma, we are aiming a bit more, right? So we don't need 2. But of course, you have a vertex where, I mean, every vertex may have some incoming and some outgoing. So this, you want to control the number of incoming edges. No, we want to control the number of outgoing edges. So let's say T is D of G, ceiling. Now what we do is we're gonna construct a bipartite graph. H on V prime, E prime. Okay. And now so these are VG. So I'm gonna have T copies of VG with no edges inside. So that's one side. And here is a E of G. So every edge. And we put an edge A is adjacent to B in H if A is a copy of a vertex. Incident with B in G. Right? So we're gonna have many edges like this. Now we claim that this H has a matching covering EG. So I want to find the matching covering that. So in other words, each edge needs to choose one end, right? And that's similar to orientation, right? So we are choosing an orientation. So what, like, choosing an orientation in a directed graph, in a graph, is like for every edge, you choose either this vertex or that vertex. You choose one of two ends to become become the tail, for instance. So this is similar. So we're gonna choose a matching covering EG, and if we do have such a matching, then that's a choice of edge, tail. Now, how many, right? So then each vertex become a, if it's chosen in the matching, then it becomes a tail of some edge. So how many times does each vertex become a tail of some edge? Well, because we make a t copies. We made the t copies, so each vertex can become tails of at most t edges. So that's why the out degree will be at most t, right? So as long as we have matching covering E, then if you use this edge, for instance, that means for edge B, we choose A as a tail, and that's the orientation we give. And each edge will have exactly one orientation because it's matching. But each vertex, since you have t copies, you're gonna have at most t edges having that vertex as a tail, so that's the out degree. So this is enough. And how do we know that H has a matching covering E of G? We use Hall's theorem, of course. Suppose not. Right? So then we let X be a subset of EG. Right? So what is NHX? What is the neighbors? Well, it's T copies of something. That is number of vertices incident with the sum edges in X. Right? Now, this gives you a subgraph. So the number of vertices incident with X and X. If we divide that, then that has to be bigger than or equal to the density, because D was, am I doing all right? The other way around, right? Yeah, this is one instance of DG. And I'm assuming that X is not empty, because if X is empty, then there's nothing to show. So because of this, and this is less than or equal to T, so that means X is less than or equal to T times number of vertices incident with X. This is equal to n of H of X. Right? So this is bigger than X. So this means by Hall's theorem you have a matching. Covering E of G. This implies that G has an orientation so that each vertex is a tail of at most T edges. And that's it. Now, how do we use this lemma to prove the following theorem of Allon and Tarski in 90s? That every simple bipartite planar graph is 3 choosable. And the proof is by Euler's formula. By Euler's formula, you know that the bipartite planar graph has at most number of edges in the bipartite planar graph is at most 2n minus 4 if it has more than 3 edges. But if you don't have, no, if you have more than 2 edges, okay, usually you may remember this theorem, right? 2n minus 4, that's the maximum number of edges in the bipartite planar graph if you have at least 3 vertices. This inequality is false if you have a 1 or 2 vertices, right? So let me ignore this minus 4, right? So E of G, then it's true for every planar bipartite graph. So this means that D of G is at most 2. So there is an orientation of G, orientation D of G, such that each vertex has out degree at most 2. Now, what is EE and EO? Right. Now, what is the number of even Eulerian subgraphs? Well, first of all, EO of D is 0. Why? If you have odd Eulerian, if D the thing is, since G is bipartite, every cycle has even length, and so every Eulerian subgraph of D has even number of vertices, even number of edges. Whenever you have Eulerian subgraph, you can decompose it into the disjoint union of edge disjoint union of the directed cycles, in this case D, and each directed cycle in D has even length, so therefore number of even or number of odd Eulerian subgraph is 0. How about even Eulerian subgraphs? The thing is, EE of D is non-zero. Why? Because there's at least one even Eulerian subgraph, namely the empty set, right? There is an even Eulerian subgraph with empty set as its set of edges. So EE is never 0. So EO is different from EE. Then we can use this theorem. EE is different from EO, so therefore D is L-list colorable for any L whose size is bigger than Di for each vertex. But the out degree here is 2. 2. So that means for every L with LV and list 3, G is L-list colorable. So this implies that G is 3 choosable. So the least chromatic number is at most 3. Okay. So that's the proof.